We're grooving. We're going to go on to liquids and solids now. There's no comments or questions at the moment. All right. Let's do some phase diagrams. They're awesome. And then we'll do heating curves. Let's do those in combo. Okay. Phase diagrams. For me, I don't know what else your other instructors told you if you're in another class. You should be able to draw either draw or interpret. If draw, you should be able to draw a basic, very simple phase diagram. So you should be able to label all the phases, put the different parts approximately, label the triple point, label CP the critical point, know where the supercritical fluid is. I mean, this is getting to about it. That's pretty much it. Oh yeah, you could be asked, it's not like part of the diagram per se, but you could be asked, where is the Clausius-Clapeyron equation represented? This line here that goes between the triple point and the critical point is the vapor pressure line because it's liquid and gas. So that's where the Clausius-Clapeyron, I put two C's there, is represented. You could be asked to draw a line on it. Like let's say you're asked to draw a line, isotherm that is below the triple point. So if you're asked to draw an isotherm means constant temperature. Isotherm. That's below the triple point. I mean, it could be wherever. This is just a random location. If I said the pressure is increasing, your isotherm undergoes what phase change, you would say? Pressure increasing. Deposition. So you should know those 6 terms for all 6 phase changes. Undergoes deposition as the pressure increases from a gas to a solid. What's a solid to a gas, by the way? Sublimation. Yep. All right. That was about it that I would be expecting. Heating curve is kind of related to this, so let's do that as well. Could be asked to draw or interpret this as well, temperature versus time. A typical heating curve would look like this. It's kind of like a ramp with a step going up 3 times. We'll do this for water, or really any would be solid, a liquid, and a gas. Here's where what is happening here? Phase change. And if you're going up in temperature, it's melting. If you're going down, it's freezing. Here's the liquid plus the gas. Going up in temperature is vaporization. Going down, condensation. Yep. This delta H is represented by delta H of fusion. This is represented by delta H of vaporization. By the way, delta H of vaporization, endo or exothermic? Positive or negative? Positive. You're putting heat into the system. Whenever it goes in, because you're boiling it or vaporizing it, then it's positive, anything going into the system. So that would be also endothermic, it's going in. Delta H of fusion, going from solid to liquid, also would be endothermic, putting energy in. How about delta H of sublimation? Endo or exothermic? Solid to gas. You have to put energy in for that to happen. So that would be endothermic. Delta H would be positive. It would be going into the system. Good, I asked. Awesome. Okay. No questions, moving on. Again, trying to go a little bit fast so you can get through all this material. Let's do the Clausius-Clapeyron. That's awesome. Whatever you want, doesn't matter. R, it's this one. To keep consistent with the units in delta H. Delta H is often given in what units? Kilojoules per mole. So you need to change the delta H over. This is just plug and chug, but many people make math errors with this one. Let me give you the couple variants of types of problems we can give you. One is just pure plug and chug. So we give you, say, 2 of one variable, say 2 temperatures, have 1 pressure, and you have the delta H. So that's pure plug and chug. You could also solve for the delta H. Any one of those 5 variables could be solved for. Another slightly harder variation is we give you, say, a known compound like water, and we only give you one state. So what would the other state be? The boiling point, which would be at the temperature 100, but really 373 Kelvin, and the pressure 1 atm. Okay, so that's called the normal boiling point. Okay, means it happens at 1 atm. So that's an option. There's another variant of this that's slightly harder. That is if we give you 3 points, but no delta H. So 3 states, no delta H. You use 2 of them to find the delta H. And the third one, either the temperature or the pressure is given. Once you have the delta H, you're going to use that and one of the other 2 points to solve. I'm going to repeat that one more time. You are given 3 points. 2 of them are fully given. You use those 2 to find delta H. Okay, 2 to find delta H. And then the third point, either the temperature or the pressure is given, but not both. So now you have the delta H, you just found it. You're going to use that delta H to solve for the remaining temperature or pressure. Those are really the variations that I've ever seen. If the person wants to get kind of crazy, this can be paralleled or put in combination in a long answer problem with any other problem that has vapor pressure. I have one on my discussion worksheet that if you're in my class, you would have seen. Let me show you something though. I think I have not done this in class yet, but this is what I'm covering on Tuesday. There are 4 types of vapor pressure problems. Let me go over all 4. Let me tell you what page this is on. 48 of my reader. So, type 1. You're given one component, like one compound. I mean by component, one compound. And one state, like one temperature, one pressure. That's what I mean by that. That you can use ideal gas law. Once you get 2 states, so one compound, one component, and 2 states, that's a Clausius platform. Again, these are all vapor pressure problems. If you have 2 or more components, like compounds, 2 or more components, and 1 state, that's Raoult's law. And then if you have 2 or more components, but it's qualitative, no numbers, then that's an intermolecular forces problem in vapor pressure. So in 2B so far, these are the 4 types of vapor pressure problems you've seen. So these can be bunched together occasionally in a long answer problem. Or done individually, itemized as shorter problems. Okay? So those are 4 types of vapor pressure problems. So that's how Clausius platform could be with one of these others. And since I mentioned it, let's do intermolecular forces, if there's no questions at this point. All right. We're grooving. Intermolecular forces. I'm going to make a little table. strongest force, top or bottom? This is generally in order of increasing force. Ionic is technically not an intermolecular force, it is intramolecular force. So you should be able to recognize any of them. Which one of these is found in all molecules? London. So, but that's not necessarily the dominant force. So you're usually trying to find the dominant force, and whichever one is the strongest of that. London has a little exception, and that's with the, I'll put capital N for the molar mass. As the molar mass increases, it can overtake the strength of the other forces. All right, this is put in combination with properties. I'll just put prop. Okay, the boiling point. Gamma is surface tension, viscosity, and Vp is the vapor pressure. Okay, as the force increases in you, then the boiling point increases, the surface tension increases, the viscosity increases, and the vapor pressure decreases. Okay? So if you're given a classic sort of problem like, and there, I'll just put two molecules. You could have multiple CHO versus CH3, CH3. Well, I'm asking which has the higher vapor pressure. So I want to know which has the highest vapor pressure. What I would do is look at each one individually and figure out the dominant force. The first one has what dominant force? So I guess this is a little tricky. Sweet. This is trickier than I had hoped, FYI. Let's do this one first. Dominant force here, on the right, is London. Woo! Oh, do you have a guess? Yeah, it's a dipole. Let me draw this out. Woo! I like that one. Wow, what did I think of that? Awesome. Okay, so which one is dominant or higher, stronger, right or left? Left. So the one on the left has the stronger force, so which one has the higher vapor pressure? The one on the right, the weaker one. Because as the force increases, the vapor pressure decreases. So the weaker one has the higher vapor pressure. All right. Oh. Okay. So that'd be a pretty classic type of problem. The other way, the easier problem would be, say, which one has a dipole? Kind of the easier version. Yeah. The first one does not have an H bond. Well, are you in my class? Okay. I don't know about the other classes. I have a pretty simple definition of the H bond. And that was I need a hydrogen on a nitrogen, oxygen, or fluorine. This hydrogen is not on any of those. It's on a carbon. So that one wouldn't count. There are more complicated versions of H bonding definitions. Maybe other classes have learned them, but I have not taught them. If you thought it was H bond, you're still going to get the same answer. It wouldn't really matter.